hello to everyone. Today we start with some harder material with respect to the other lectures, which were giving an overview of empirical studies in software engineering. Now we start with one of the strategies that we listed last time, and these controlled experiments. Here I've put a couple of references that you can take for to extend the material that you will find in these slides. We will go through this topic in this lecture and in the next lecture, in which I will show you guidelines on how to select empirical tests for controlled experiments. So last time, to take a bit from last lecture, we saw the different types of research strategies, and we saw that experiments, laboratory experiments, controlled experiments, in vitro experiment as a paradigm, are typically strategies that require a contrived setting, so an artificial setting, okay, not the natural one. A setting in which I am, for example, in the lab. Of course, for software engineering experiment, it doesn't necessarily need to be like a scientific lab, but at least a room or a space in which you can eliminate some confounding factors or some confounded variables, as we will see in the next slide. So the goal, when do you use a controlled experiment? When your goal is to measure the behavior in a precise way. The behavior of whom? The behavior of actors. Actors can be, as we said last time, both software engineers, but also tools, okay? Precision is the core. And it is also important to highlight that this behavior needs to be related to quite clearly identifiable variables. So if the variables that you want to measure are too complex and are affected by several factors in practice, it is very unlikely that you will use an experiment. It's more appropriate to use a field study, okay? When you can isolate your variable, and we will see some examples, it is appropriate to use an experiment as a research strategy, okay? We speak about controlled experiment, but you will find also synonyms in the literature, so laboratory experiments, but also simply experiment, okay? But they refer mostly to the same thing. We will discuss next time a little bit about the concept of quasi-experiments, but we are speaking about the same practical cases. Okay, let's start with some practical typical examples that can give us an overview of what we will be speaking about in this lecture. Experiments, they can be in software engineering, at least, like because experiments, of course, we study them in this specific field. They can be with software subject or with human subject. So, for example, experiment with only software subjects are like the one that is described here. I have two tools, so one tool A and one tool B, and they do automatic testing. Okay, they are push button tools for testing. So I have some code, I press a button, and the tool tests my code. And I want to compare them. I want to compare them in terms of different aspects. For example, how many bugs do they find, and how fast they are in finding these bugs, etc. So I need to compare two tools. In this case, since they are push button tools, fully automatic tools, I do not need to involve people. Okay, so it's an experiment with only software subjects. When I have to involve human subjects, it is the case, for example, only human subjects, so no software subjects involved, but still in the field of software engineering. There is the second example. So I have a certain method that is a manual strategy for finding bugs in the code. So I manually review the code, and I search for bugs according, I don't know, according to a certain checklist, for example, a new checklist for finding bugs or also other defects in the code. My question can be, how effective is this guideline, this checklist for experts, and how effective is it for novices? Okay, what is the differences between novices and experts in adopting this type of method? So here I'm involving human subjects. I'm studying constructs related to the subjects, because is the level of expertise here that I'm studying actually. And I want to see how a certain strategy, how the behavior of the people varies when using these specific strategies. Okay, specific strategy varies in terms of effectiveness. So this effectiveness can be again defined in different ways. So how many bugs do they find? How quick are them in finding bugs? So, but the idea here is that while in the first example you have only software subjects, in here you have only human subjects and a strategy. Okay, but most of the time you mix them. Of course, you have both software subjects and human subjects, because fully automatic tools rarely exist in software engineering. So it is more likely that you have an interactive tool for testing, and you want to see if it is more appropriate for novices or experts. Okay, like the example before, in which you have a method, but in this case you have a software tool. Okay, but you can have also other more complex cases. So you have two tools, one both interactive, and you want to compare them. So in this case, you don't care about the level of experience, so novices and experts. You just want to compare them, but you need to involve people because they are interactive tools for testing. Okay. And in this case, how will you select these people? I will select them if I assume that these tools are somewhat independent on the expertise of the people. I need to involve people with various expertises and in a balanced and general way, so that my sample of people is somehow representative of the typical typical population of developers. So that somehow I eliminate, I get rid of the expertise aspect in these experiments, in this specific experiment, and I just compare tool A and tool B like they were automated tool. Okay, although they are interactive. Okay, this is the general idea for this type of experiments. We will see more in detail this type of little tricky aspects when we will see more detailed examples. You can have also other cases. Again, you have two interactive tools, and in this case you want to see which one is more appropriate for novices and which one is more appropriate for experts. Okay, so expertise now becomes again a relevant aspect to consider. Or you can even compare tools and approaches. So for example, in a company I may use a typical code review strategy with a certain checklist, and I want to introduce a certain tool A. Okay, I am comparing a tool and a method, and I want to see which one is better. Again, this is an experiment that involves software subjects, so the two, but it also involves human subjects, because I need to recruit people that actually use these approaches. Okay. Of course, things become trickier if the tool is fully automatic, and the method, of course, requires some manual intervention. So you need to really take care. You need to carefully consider the variable that you are evaluating in this case. These are examples, and now let's see how these experiments are placed in our diagram of theory building in software engineering and in science in general. Basically, controlled experiments are positioned, are deductive approaches, so are positioned in the top-down direction of this diagram. So they are not using induction, but they're using deduction. I have a certain theory, okay, a certain theory taken from the literature or observed from previous a more exploratory study, and I formalize some hypotheses from this theory. And then what I want to do is to test the hypothesis. So in this lecture, you will see how to approach this all deductive process, okay, that we saw last time in the context of theory building with induction, abduction, and deduction, okay. What is the process for controlled experiments? And at the end of these two lectures, I will show you more in detail what all these blocks mean. But the idea is that taken from the previous slide, in which you start from some theory and you go down towards the observation of reality, here the situation is similar. So you start from the theory, you build some research question in the way that I explained last time. You create hypotheses and variable definitions, so you operationalize the constructs of the theory through variables, as you remember the terminology that we used. And we do our research design. That means also selecting the type of of how many groups, for example, of people do I want to involve, and how to map these variables into actual data that I can gather, okay? And in the research design, I also define the measures for the different variables. Then I recruit the participants and I select artifacts for my experiment, collect data, analyze data. This is the execution of the experiment. And then I discuss several validity threats that are all related to different layers, to different levels of my study. I report my answers to the research question. And finally, I discuss how the theory changed based on my experiment. So I start from a theory and I perform this study. So I go top down towards reality. I test the theory, really test in a quantitative way, and then I discuss if the theory is confirmed, in which way it is, in which way my scope of validity is extended for a certain theory with respect to previously existing studies. And so basically discussing in the end means comparing with existing work in the field and explaining in which way your experiment advanced the knowledge in that specific field, okay? This is just to give you an overview of what controlled experiments are and how are they positioned in the process of building theories, okay? Now let's see more in depth what are the elements that you will learn in this lecture. Okay, here you will see a lot of words that you probably do not know, and they are the core elements of the approach, of the controlled experiment approach that I'm going to explain. So one fundamental element, this picture, you have to read it starting from design, collect data, and afterwards analyze data, okay? You start from a certain hypothesis that is derived from the theory. If you remember, we had propositions in the theory that can be translated into some form of hypothesis. We will see examples of hypotheses later on. Then you have the concept of independent variables, dependent variables, and control variables. This is the identification, the operationalization of the so-called constructs of my theory, and I have different so-called treatments. Okay, we will see what are the treatments in very few slides. Okay, so basically this is the design that is somehow transforming your theory in something more operational and more controllable. Okay. Then you collect the data, so you measure this variable that you have defined, and you have all your data from the experiment. So the experiment takes place after you designed, it takes place, and afterwards you have a lot of data and you have to analyze them. So in the rest of the picture, you have all the concepts that are needed to analyze the data. In controlled experiments, analyze the data most of the time means doing hypothesis testing. So quantitative tests of the hypothesis according to some statistical tests. you take, what is it, a statistical test? For you, it is generally a black box in which you insert a certain significant value, a value that indicates how sure you want to be of your results, basically, and outputs three main values, two main values, and another value can be computed later on, but two main value. One is the test statistic, that is a numerical value that doesn't mean so much in itself, but is the main output, let's say, of the test. We will see the meaning, the specific meaning later on. And the p-value. The p-value is a value that, while significant, tells you how sure you want to be about the results of your test. The p-value indicates basically how sure can you be about the value of the test once this has been performed. Understanding this concept of significance and p-value will be not straightforward, but I will do my best to show you pictures and some graphical diagrams to allow you to understand them at best. Another thing that you can extract from this analysis, analyzed data, is the effect size. So, for example, the test can tell you how significant is your results. So, how sure can you be that your test is successful? So, how sure can you be, for example, that in this case, normally that your null hypothesis is rejected, but this we will see later on. But how sure can you be of the conclusion of this test? And the effect size is how much is this effect that I'm measuring with my test large, okay? So one is the p-value output telling you how much can you be confident, let's say, how significant is your result, and the effect size tells you how large is the effect that you have observed in your data. Okay. After this analysis, you have more confidence about the reliability of your hypothesis. So actually, we are never speaking about accepting an hypothesis, but we are speaking about rejecting an hypothesis, and we will see this in the next slide, some explanation about that. But the idea here that you need to remember is that you start with an hypothesis that you don't know whether it's true or not, and at the end of the data analysis, you may have come to a result that tells you this hypothesis is more likely to be true than to be false. Okay. The left part will require your creativity. So designing and also collecting data somehow, because it involves selecting also the people involved in the experiment, because most of the time you will deal with human and software all together, requires your creativity. You have to invent how to pass from your research question to variables, and you need to justify the measures that you are using for the different variables. Okay. And this second part is mostly automated. As I said, the test for you as a software engineer will be mostly a black box. But you need to understand what are these concepts and how to interpret them, because there is some statistics in them, and is not fully straightforward. Okay. So let's see more in detail what are these controlled experiments with some definition. Now we've seen a bit of a high-level view of what are the different elements that you will encounter through these lectures. Now let's see more formal, let's say, definitions. Okay. A controlled experiment, let's read the slide, is an experimental investigation of a testable hypothesis, in which conditions are set up to isolate the variables of interest that are independent variables and test how they affect certain measurable outcomes, the dependent variables. So what does it mean? Look at the picture, and I think it's quite intuitive. You have some input variable, okay, some input variable that you want to change, and these are the independent variables, okay? The experiment is this box, okay, the treatments box, let's call it, and you want to see how certain dependent variables, so variables of output in this box, vary based on the independent one, okay? The treatment, what is a treatment? A treatment is a combination of values for the independent variables. What does it mean? An example can clarify everything here. For example, in the case of the experiment with software tools, I may have the independent variable is the testing tool that I'm using, okay? The treatments is one treatment is with tool A and the second treatment is with tool B, because the testing tool as a variable can take tool A or tool B as values, okay? So I have two different treatments. And the dependent variable is the thing that I want to measure. For example, can be the number of bugs found in the software or the speed. Okay, this is the basic element of any experiment. So independent variables that are also sometimes called factors. Okay, the treatments that are combinations of values of the independent variable, and the dependent variable, so the measurable outcome that I want to observe. So I change something and I want to observe something as output. It is important to consider this other part. What I want to do is to isolate the independent variable, because I want to see just the effect of them on the dependent variables. Okay. So this means that in the whole experiment, in all the treatment, all the other variables need to be controlled, okay? So in the example of the testing tool, what I need to do is that what can be the other variables that can affect my dependent ones, okay? What can be the other aspects, the other factors that combine with the choice of the testing tool can modify the number of bugs found? Well, obviously, the type of code that I'm using for testing, okay? The code sample that I'm using for testing. If these code samples need to have a sufficient variation of number of bugs so that I can see, so that they are sufficiently representative of typical code base, okay? So I need to control the variable of number of bugs in code, but I have also a number of bugs, like not number of bugs found in terms of dependent variables, but number of bugs included in the code that I'm considering in the experiment, included in the code sample, but also the length of this code sample, because in reality I can have different lengths, and this may affect, for example, the speed of the tool, or actually the number of bugs that a certain tool is able to find. Okay, so this is to tell you that here like in any controlled experiment, the independent variables need to be isolated if I want to say that the variation on the dependent variable is due to the modification of the independent one. Otherwise, if I don't control these variables, what happens? It happens that I may observe variation in the dependent variable, but this may be caused not by the independent one, but by the other variables that I didn't control. So it's like being somewhat in a field study where I take things from reality, I don't isolate elements, and I see their collective impact on a certain variables, but of course, the validity of what I'm finding and the connection between independent and independent variable is much weaker, okay? So it is really important to remember this when you design an experiment. So again, this is highlighting a little bit more what we mean by controlled variable here. For example, I was listing the sample length, the type of language, also because some tools may be working in only on a certain language, the degree of complexity of the code, because also this may impact on the ability of the tool to find bugs. So all these variables need to be controlled. They can be related to objects, like in this case. In this case, they are related to the different code samples that I'm using in the test, in the experiment. And they can also be related to human subjects. In this example, I'm using software subjects only, but if humans are involved, as I briefly touched before, you will need some representatives of different types of developers with different expertise. For example, if I want to make this experiment independent of the expertise of the people, so I need to control the expertise variable. Okay. What are the main characteristics that the controlled variables should have, and at least the sample that I'm including in this experiment should have? They should be equivalent for each treatment, so not equal, but at least equivalent. They can be, they should be general enough, so to cover with my experiment the largest part of my scope of interest. And homogeneous. They need to be homogeneous, of course, is another way of saying is a way of saying that they are not emphasizing any aspect. If you are using, for example, a code sample, you cannot have all the code, all the C code of a certain length, and all the Java code shorter. Okay, you need to have some homogeneous representation of all the different factors in the sample that you consider. And representative. Okay, they need to represent some reality. Okay, they need to be representative of some population of code in this case. Okay, so it's very difficult to do this selection, and you need to justify your selection. And very often, if especially the control variables are many, you end up dealing with the need to constrain some dimension. We will see an example later on. So when I consider human subject, as I simplified before, the control variable may be related to the experience of developers, for example, so or age, or like gender, or like if you are using biometric sensor, also the color of the skin may affect that. So there are several aspects that may be considered to have to control your variables. Okay, so let's go to some more formal definitions. Okay, you have now a general understanding of what we are speaking about here, but now we give some definition, and I will generally read what's written here. So we start with the definition of hypothesis. The hypothesis is the statement that I want to test with my experiment. So as I've shown, I start with the hypothesis, and at the end of hypothesis, at the end of my experiment, I have either rejected my I have either rejected a certain hypothesis, or I have some support for that hypothesis. Okay, the hypothesis is normally derived from a research question. For example, what is the difference between A and B in terms of bug detection capability? The same example as before. So is it better A or B for finding bugs in this code? Okay. I then include the hypothesis include variables that represent my constructs, the constructs of interest, that may be tools, methods, actor, number of bugs. So all the things that may be involved in the experiment and that are relevant for me. And the hypothesis normally concern the measurable impact that a certain variation of some construct can have on other constructs. Variation in input variable can have on output variable. So variation of independent variables can have on dependent variables. So tool A finds more bugs than tool B, or tool A finds less or equal bugs than tool B. Okay, these are examples of hypotheses that are derived from the research question and that are concerned with a specific construct in my experiment, in my scope of interest. Okay, and when we do a hypothesis testing, we normally have a null and alternative hypothesis. Okay, the null hypothesis is the one that I will test. Okay, but the one that I am interested in is the alternative one. Okay, this is a tricky thing that you at this moment you will have to take as a fact. Okay, when you do hypothesis testing, you're actually testing a null hypothesis that is telling you the exact opposite of what you want to show, but it will become a little clearer later on. Okay, at the moment you just take it as an assumption. Okay, so more definitions. Again, you already understood what are independent, dependent variables, treatment and controlled variables, but here you have precise definition. So independent variables are operationalization of constructs that I want to isolate and whose values I want to manipulate. With the example, you see this is clear. I want to isolate the type of tool so that I want to see just the influence of tool, or I want to isolate the expertise of actors so that I just consider that, and I want to manipulate because I do different treatment, because I assign different values to these independent variables. Then I have treatments that are actually combinations of values for the independent variables. So here I have, if I have tool A and tool B and I test them and I compare them, I have one variable, the type of tool, and two treatments. Okay, normally you speak about one factor, two treatments, or one variable, two treatments is equivalent. Okay, but in the books you always find one factor. Okay, actually you find quite frequently one factor, two treatments. Okay, but don't get confused with this. It's just synonyms. Okay. Or you can have, if you want to consider also the expertise as a variable, you will have for treatments, because you need to experiment with tool A and experts, tool A and novices, tool B and experts, tool B and novices. So you have two variables and four treatments. So you see that your design can easily get complicated, because when you have just the tools and one variable, you just run the experiment and you compare between two elements. In here, you just added one variable, that is the expertise, but you involve people, you need more effort, and in addition, you have four treatments. So you need enough people also to carry out this experiment in four different groups. One group using tool A, one group of experts using tool A, one group of experts using tool B, etc. Okay. Dependent variables. Dependent variables are the output, and they are operationalization of constructs that I want to measure based on the manipulation of the independent variables. Okay, so these are the operationalization of those constructs that vary based on the independent variables. Okay, for example, the number of bugs. And finally, controlled variable. We discussed them extensively, and these are again operationalization of constructs, but in practice they are attributes of human subjects or objects, as we saw before, that I need to control to mask or prevent their impact on the dependent variable. This controlled variable, I need to control them, because otherwise the variation of the dependent variable is not linked only to the variation of the independent one, but may be caused by this other variable. Okay, and for example, as it was exemplified multiple times, I have to test on some code that is sufficiently general and equivalent for all cases. Let's see an example. You've seen these examples somewhat hidden in the previous explanation, but now let us see it more extensively. So this is an example of an experiment, of the experiment with just software. Okay, my goal is to understand which tool is better for testing among two available choices, A and B. Okay, these are push button tools, so I don't need to consider the impact of the human in using this tool. Okay, the independent variable, we already saw it, is the tool, is one factor. Okay, the treatments are also straightforward, so I have tool A and tool B, one factor, two treatments. What is the dependent variable? Well, my objective is to see which one is better. What do I mean by better? Okay, better is a quite vague concept. Is it better in terms of speed? Better in terms of bugs found? I want to consider both aspects. So in this case, I will have two dependent variables, and I define them as effectiveness and efficiency. So I compare the two tools in terms of effectiveness, that is, how many bugs do they found, compare with the total number of bugs that is present in the code, because in this case, I assume that the tool could not be able to find some specific types of bugs, and efficiency, that is related to the running time, and I define it as the running time in relation to the number of bugs that are found. Okay, or I could define it also in relation to the length of the code. This is just what I decided. I decided these quantities to mean. Okay, I decide what I'm interested in. Okay. In this case, I have these two dependent variables, one dependent variable and two treatments. Okay, now comes the difficult part. I have to identify the control variables. And the question that I need to answer is, what can impact on effectiveness and efficiency beside the type of tool? Well, the user, we said, no, it doesn't impact because the tool is just a push button tool, it's fully automatic. The language of the code, yes, then probably it is too hard to consider all the type of codes because I would need a too large sample. And in addition, one of the tool is able to test just for C. So I want to focus just on C code. So you see that I'm reducing my scope of interest somehow. Before I was speaking about difference between tool A and tool B in finding bugs, but now I am saying that I'm focusing just on C code, on a certain type of language. Of course, also another variable to take into account is the chosen code, but the chosen code sample, as we exemplified before. So, but which are the attributes of the chosen code that may have an impact on the dependent variables? Where might be the actual number of bugs in the code module, so I need some sufficient variation in terms of number of bugs in each module that I'm testing. The length of the module, as I said before, some tool might be more effective if it's working in shorter code, so I need a quite different and realistic representation of different codes. The complexity of the code, another variable, and the domain of the code. Why? Because maybe depending on the domain, I have certain type of solutions that are always adopted in a certain code, and a certain tool is more appropriate for the features that the code in that domain shows. For example, in a safety critical environment, I may not be allowed to use global variables, or I may not be allowed to use pointers. Okay, so a certain tool may be more effective for the specific quality, specific feature of the safety critical sector, of the railway sector, for example, while it may not work properly if the C code has pointers and has other characteristics. Of course, you can frame it in different ways. You can look at the different characteristics of the code, or you can just say, okay, this code is coming from a database of railway code, and this code is coming from a database of I don't know, financial software. Okay. So these are all variables that you need to take into account and justify when you design your experiment. Okay. So as I said, I have to create a code sample that has sufficient variations in all these variables. And if I cannot vary a certain variable, if I cannot have a sufficient variation in a certain variable, I have to fix it, like I did with the C code, or like I might need to do for the domain. Okay, and I need to make this choice explicit, as it limits my scope of interest. Okay, or in this case, if the theory, it depends, it may limit your scope of validity as well. But in this case, you can say, okay, my theory, I want to refocus my theory only on this domain and on this type of code. Okay, so this creates a boundary. So the controlled variable somewhat create a boundary in your scope of interest. Okay. This is another example with software and humans. Okay. And in this case, like it is an example that we considered also before, I want to see if the experience of the user affects the effectiveness of a certain tool. Okay. The dependent variable in this case is the one that we took from last experiment. So is the effectiveness, that is the number of bugs found divided by the total number of bugs in a certain piece of code. So this is the dependent variable that I want to observe, while the independent variable is the experience of the user. But the issue here is how can I measure this experience? While before the independent variable was tool A or tool B, it was quite clear, straightforward. We didn't even think about measuring the independent variable because it was a binary variable, basically. So either you use tool A or tool B. But in this case, your independent variable is the experience. And the issue is how to measure it. I can consider, how can I measure the experience of a user? Where I can consider the years of experience in testing, or I can ask what the years of experience may tell you something, but they don't tell you how expert is really that person. So you may want to ask the colleagues to judge a certain person and to score this person for expertise in testing. Okay. So in general, it is better to select one independent measure for the variable. Okay, so otherwise I may need too many treatments and might not find enough participants. Okay, so better to select one of these measure and justify it. But okay, so let's consider, since it is easier to evaluate, although not necessarily perfect, I consider the years. But should I consider 1 year, 2 years, 4 years, 5 years? So by single year, or can I group this year? Well, if I decide that I choose 1, 2, 3, 4 as differences, so I want to see how a difference of 1 year only can affect the usage of a certain tool. Well, this may be difficult in several terms because maybe the difference between 2 and 3 years of experience is not that much. And in addition, I need to find enough people for the experiment. So I have to find many people who have just 1 year, many people who have just 2 years, many people who have 3 years. And so it may be very complicated again as an experiment. So probably it's better to separate, to select some levels. Okay, how to select the level? I have to do some assumptions. Okay, I have to take some assumption, take from the literature, or justify and defend my decision. Okay, there is no silver bullet in here. Okay, and often you resort on other studies that have done a choice that is similar to yours, or you have to consider also common sense and your knowledge. For example, I can decide for 2 levels. Okay. And in this level, I have 2 treatments. One from 0 to 1 years novices and more than 5 years experts. Okay, so in this case, I have eliminated people that are in between. Okay, there is a radical difference, of course, between 0 to 1 year and more than 5 years. Okay, so this is evident, and it is common sense that I don't need to just justify much. Okay, so think about that. Of course, if you have people that have between 2 and 4 years of experience, and these are candidates for your experiment, you cannot use them. You cannot involve them. Okay. Now I have to identify the control variables. Again, the question is the usual one: what can impact on my outcomes besides the experience? Here, I don't have the code, I don't have the objects, but I have people. So in this case, I can have age, gender, demographic variables. So how old are them? Where do they come from? Where did they study? Okay, from which company are they coming from? And of course, again, the code on which the tool is applied. Okay. So the other previous variables. So you see that this experiment becomes much more complicated. I have to make some choice. I fix some code base. We use the same for all subjects, and make sure also in this case, since I have also interacting aspects, make sure none of them have seen the code in advance. Because if, for example, if I have to test certain code that I have already tested, I know already which are the bugs. So this is affecting my experiment. So but in some cases it may be the case that if you're using code from a certain company and the people are from the same company, it is possible that those people have seen that code. Okay, and this jeopardize your experiments. Okay. And then I control demographic variables. Okay, I select the variables in a way that I have a representative group of people without imbalance in terms of age, for example. Otherwise, if I cannot do that, again, I restrict my scope of interest. If I find just people, for example, in that are all coming from the same company, of course, the result of my experiment is limited to the characteristic of the specific company and may be extended to companies with similar characteristics and with similar trainings, for example. Okay, so at the end, this is my design, and I have a group with a comparable experience, novice or expert, but variations in terms of age, gender, and other demographic aspects. And I have a code base. So I have designed my experiment. You see that here, when I said this requires a lot of creativity, it requires a lot of creativity. You have to think thoroughly about what are your constructs, how to measure them, how to create your variables, how to measure the variables, and you have to consider different factors that are also related to the possibilities that you have. Because when you build a software experiment, a software engineering experiment, you don't have infinite resources. If you are using, for example, if you are involving developers, and as we said in the last lecture, these developers, they have to do their work, their daily work. So they cannot stay in your experiment for 2 hours. And there are also fatigue and other factors that may affect the experiment. So it's really, again, optimizing between different factors. Okay. So what are the pros and cons of controlled experiment? The main advantage of using controlled experiment is that you are doing real science, okay, with the numbers, because controlled experiments are quantitative. But up to now, you didn't see any number, okay? You didn't see any number, so you see that they are real science with numbers. But real science means also dealing a lot with creativity, with creating this constrained environment of the lab experiments, of the controlled experiment. Okay, and the great advantage is also that they can be applied to identify cause-effect relationship for specific, well-defined variables. Why? As we said before, the goal of the experiment is to isolate the independent variable and control the other one, so that the dependent variable is just dependent on variations of the independent one. Okay, so this allows me to say, when I change this, I have a change in that, and this change is not caused by anything else. Okay. Disadvantage, there are many. Okay. They are applicable only to well-defined problem in which you can actually define and isolate these variables. As I said at the beginning, if you have cases in which it is very complicated to isolate the variable of interest because the contextual factors that may affect them are many and cannot be separated by the measurement of the variable, it is very hard to perform an experiment. And they are hard also if you cannot simulate the right conditions in the lab. So if the confounding factors, confounding variables may be too hard to control, so the other variables that may impact the dependent variable. And the other issue is that the experiment is not realistic. The behavior, especially the behavior of people in an experimental environment, is way different from their behavior in the real world of software development. But the obvious thing is that while in a lab the experiment is carried out and it lasts maybe 1 hour, 2 hours maximum, also because afterwards people get tired. In software development, you have 8 hours of programming in a day or even more, and in addition you are dealing with a dynamic and ever-changing context with several people coming to the developers, emails coming, requests coming randomly. So it is a much more complex reality that changes the behavior of the developer and that influences the behavior of the developer. And of course, recreating this complexity in the lab is not possible, even just for the matter of time. Okay. Another issue is that if you do an experiment with human subjects, it is hard to recruit the subjects. Of course, as I said, developers have to develop and managers need to manage. So people have to work. Okay. And recruiting people, for example, with expertise higher than five years is complicated. Okay. And very often in controlled experiment in software engineering, students are used. Okay, either PhD students or master students. Okay, they are proxies of real world developers, but of course, in practice, they can rarely mimic the degree of expertise. Okay. They are used as proxies when you want to test, for example, a new methodology or a new tool that you are proposing for software engineering, for software engineers. But they are used because it's easier to involve students, and it is less costly to recruit them because you may pay them a little money or a little reward, a thing that is always important to give in an experiment. You always have to think, hey, but this person, why is she or he coming to the experiment? Either for learning something, either because this person is forced, but you don't want that, of course, or because you give them a kind of soft reward, or because they learned something from the experience. Okay. So you have to carefully consider this when designing the experiment and thinking about recruiting. As we saw in our example, the design is time-consuming. We spent a lot of time thinking about the experiments and can get very complicated very easily. Okay, so if the thing becomes too complicated, the actual control becomes difficult. Okay. So better, the recommendation here is that better to keep your experiments simple. Okay, otherwise your controlled experiment frequently risks to go out of control. Okay. So now we pass to hypothesis testing, but now first let's make a little break. Okay.